So we are now in the part of the course where we are going to look at proofs. So one misconception that students might have when we are doing this part of the course is that the goal of this is to learn those theorems. We are not really learning those theorems. Besides, the ones that we are doing are not really much of theorems. What we are trying to do is to understand what proofs are and how they are structured, and use our understanding of logic and rules of inference in order to be able to read them and understand them. And while you're reading proofs, I don't really want you to memorize what it says and what the final result is and what theorems we are proving. But I do want you to look at the proof and say, aha, so here, this step is because of universal instantiation. And in this step, we use the definition. And in this step, well, it follows by universal modus ponens from the previous one. And again, chances are we will be skipping some steps. If you think a step is skipped, try to work it out yourself. So let's do a proof example with hopefully as few skipped steps as I could think of. So remember when we introduced contrapositive of a formula, we said, oh yeah, if you write not B implies not A, that's the same as A implies B. And we had some kind of calculation to justify our claim. Let's look at this proof again, now with the knowledge of what different rules are, and see how different steps use different rules to get the final answers. So our theorem, kind of small theorem, says that for any propositional formulas A and B, not B implies not A is equivalent to A implies B. So let's now prove it. First, it starts with saying for every propositional formulas, for every A, B in the domain propositional formulas. In order to prove a statement like that, our first step is universal instantiation. We want to give them names. And by the way, a lot of time in proofs in computer science and mathematical literature, people wouldn't even bother to give those variables different names. They just say, okay, let A and B be arbitrary propositional formulas. But pay attention that here it does mean something different. Before, A and B were kind of standing for everything. It was a variable. Here, we're thinking of some kind of concrete, but we don't know which propositional formulas. Something can be true, something that can be false. And because we are thinking of them as concrete things, we could talk about what happens if A is true, what happens when A is false, and same for B. So this is what universal instantiation does for us. So our next step was to say, let's get rid of the implication. Implication is confusing, and rewrite it as a not first thing or second thing. So we rewrite not B implies not A as not B or not A. You've done it multiple times, and you know that you could do it because by definition of the implication, F implies G is equivalent to not F or G. Next step, we could use the double negation axiom. So look here, we are using the actual axioms of logic to get rid of the two negations in front of B and obtain B or not A. Again, we've done those steps before. We've done those proofs, but now what we are doing is to see how we got every step from the next step. So finally, we have another axiom which says that for any formulas F and G, F or G is equivalent to G or F, and so we could switch around not A or B, B or not A. So we got not A or B, and our final step, we appeal to the definition of implication again, and this time to convert an or into an implication, not A or B becomes A implies B. And now we are done. So we started with not B implies not A, and through the chain of equivalent, 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 we got A implies B. And therefore, because of another axiom which says if something equivalent to something and that equivalent to something else, then all the things in the chain are equivalent, in particular the fourth and the last one are equivalent. Well, you kind of knew it, but let's spell it out. By that property, not B implies not A is equivalent to A implies B. So now, finally, we do our last step, universal generalization, to say that because we didn't use anything about A and B other than that they were propositional formulas, this is true for any formulas A and B. And now we are done. So again, the point of this is not to convince you that not B implies not A is equivalent to A implies B. We are doing this to see what are the logical steps involved in this proof. So when you read a completely different proof of something else, you could say, oh yeah, I've seen that step before, that's a universal instantiation step. And oh yeah, this is probably by the definition of something, and this is by an axiom. So this particular type of proof has a name, it's called a direct proof. And this is the most direct of all the types of proof we are going to look at. This is when you want to prove that for every x, f of x holds. And you do it by showing that f of x holds for some arbitrary element n in S. So in the previous example, instead of one x, we had a pair A and B, but it's the same thing. And we started with universal instantiation. Let n be an arbitrary element of S. Let A and B be arbitrary propositional formulas. And then use axioms, definition, previous theorems to show that f of n is true without any extra assumptions on n. And finally, your last step is to refer to universal generalization to conclude that for all x, f of x is indeed true. And then we are done. So often you see that little square at the end of the proof. It means done. So one special kind of direct proofs is when your f of x is of the form something implies something. And in this case, we actually shortcut and we skip a step. Or should I say, a lot of time when people prove statements like this, they shortcut and skip the step. But let's see what step they skip. They often you read a proof and it will say, let for every something implies something, assume and take an arbitrary element for which the first thing g of x is true, and then derive h of x. So the step that they're skipping here is the following. Really, your universal instantiation just says, let's take n to be an arbitrary element of S. G of n can be true, g of n can be false. Why aren't we talking about g of n being false? Well, if g of n is false, then we are done, because false implies anything. So g of n implies h of n for trivial reason if g of n is false. But if g of n is true, well, then we are talking about n for which g of n holds, and now things get more interesting and complicated. So again, here's one example where there is a step where people commonly skip because the proof of that step is kind of trivial and people sort of know it, and so they go to the interesting part right away. So again, when you see a line, let n be arbitrary element of S such that g of n holds, think about it as, there are several parts here. There is a skip step, but I know what this step is, so I'm fine with it. So another thing that you see a lot in those proofs, and you see a lot in general, is definitions. So what is a definition? Let's define a definition.